Good evening, everyone. Welcome to the week 6 live interaction session. Let's just wait for a few minutes for others to join before we begin our session for today. Let's just start our session for today. Let me just share my screen. So before starting, can anybody confirm whether the screen is visible and I'm audible? Anyone? Okay, thank you. So let's just start our session. Okay, thank you, thank you. So let's just start our session for today. Good evening, everyone. Welcome to week 6 live interaction session for the course Colloids and Surfaces. This course is offered by Professor Basavraj from the Department of Chemical Engineering, IIT Madras. Myself, Pratyumnan, from the Department of Chemical Engineering, IIT Guwahati, Assam, is one of the teaching assistants who is responsible for conducting the live interaction session every week. So we have come across 5 lectures where we discussed, again, just as a recap, we discussed about the fundamental concepts, properties, different forces, interactions. Then we discussed on the van der Waals forces of interactions in detail, where we discuss on the different types of interactions such as Keystone interaction, Debye interactions, and London dispersion forces. After finishing that concept, last week we discussed on the Helmholtz electrical double layer. So I hope you guys remember about that particular concept on Helmholtz, because that forms as a base for the different types of models that we will be studying this week and the upcoming week also. So So if you see in the right hand side, we saw through the figure that is towards your extreme left, right? So this is something that is representative of the Helmholtz electrical double layer. So if you are able to recollect, we discussed that the Helmholtz electrical double layer concept is based on the principle that the counter ions, so we discussed about two different types of ions. One is the coions and another one is the counter ions. So coions have the same polarity as that of the surface, and counter ion have opposite polarity, or oppositively charged compared to your surface under consideration. So these counter ions get absorbed onto the surface of your uh, onto the surface of your colloidal particle. So this absorption is something that is necessary so that the electrical neutrality in the system can be maintained. So this is fundamental. In any system that you take, the electrical neutrality should be maintained, or otherwise the system is kind of like unstable. So in case of Helmholtz, we discussed that the oppositively charged particles are directly adsorbed onto the surface, and then this adsorption helps in maintaining the neutrality in the system. But again, this comes with a particular limitation. So when this model was proposed, it had a particular assumption. So that assumption is that all the charges are adsorbed onto the surface, and these charges that you see are rigid monolayer charges which are adsorbed onto the surface for maintaining electrical neutrality. But then the question comes here is that when you place these kind of surfaces or any kind of charged particle in the solution, will there be, will there not be, to be correct, will there not be any kind of other effects that will happen in the solution? So when if so it's like, we can take a small example. If you for example take a beaker, and in the beaker you just, let's say, drop some ink or any other kind of material. So always there will be some movement, right? So once you drop some particle inside the solution, there will be a movement. Or to be correct, if you take the example of water, and then if you drop a ink inside this beaker, then there will be diffusion, right? So any kind of ions that are present in the solution will also be having some sort of a diffusion motion. So there will be some thermal movement always happening in any solutions that you take or anything that you add to the solution. So these electrolytes, or you can say electrolytes are nothing but charged solution, or the solution that contains charged species. So any electrolytes will also have these kind of diffusion and the thermal motion. So that particular concept of diffusion and then the thermal motion was neglected, or to be very honest, was ignored when the Helmholtz model of electrical double layer was proposed. So after, you know, lot of research and over the period of time, they found that this particular limitation has a significant role in the mechanism of the electrical double layer formation. So after which this Helmholtz electrical double layer model was further improved by taking into account the thermal diffusion and then the yeah, thermal motion and then the diffusion of the electrolyte ions to the surface. And that's what you can see here. If you see the figure B, you can see that there is a, compared to the spacing between the positively charged and the negatively charged species in case A, in case B, that particular distance is quite large. And you can see this negatively charged ions that are attracted to the positively charged surface. Along with those, you also have this, uh, what do you say, solvated cations. So these are nothing but the solution molecules which are also present, and this is predominantly because of the thermal motion or the diffusion motion that happens in the solution. And this was taken to be one of the most like kind of a model that accounts for all the real life situation that is happening in the solution. So this is, so from here it, the concept of diffused double layer model actually starts. So here you can see some of the equation which we will discuss within a few minutes. But yeah, this is the difference between the Helmholtz and then the diffusive layer diffusive electrical double layer model. So from here we can have, you know, it accounts for all the kind of possibilities, that possibility of you know, it does majority of the assumption that was taken in the Helmholtz double layer is removed now. So this is something more realistic compared to the Helmholtz electrical double layer model. So this principle is something that is exploited in variety of applications. So if you remember in the last class, we discussed about the concept of energy storage. So that's what you see here, electrochemical energy storage. Something which we discussed was on supercapacitor, where they use this principle of electrical double layer in order to in order to store charge. Similarly, there are also other fields which uses the principle of this electrical double layer. So one thing is the electrocatalytic system, and then another one is the electrophoresis and surface adhesion. After that you have is the electrical double layer transistors, colloidal suspension and electrification, and then you have the mechanochemistry. So you can see the importance of this concept and how this concept of electrical double layer is getting exploited, or like, you know, is used in multiple application for realizing many, I mean it's used for as a beneficiary concept in many of the different applications. So if you are interested, obviously you can always, you're always welcome to go through how does this electrical double layer is helpful in all these application, and how I explained in the last class about the electrochemical energy storage, where we discussed about the separation that happens between the positively charged and the negatively charged molecules, like you see here. So positively charged surface and then the negatively charged molecules that is formed near to the electrode surface. So this two surface together looks like a electrical double layer, and then these ions are separated by the solvent molecules. And since these solvent molecules are very small, the distance between this positively charged and the negatively charged layer is also very small, and this leads to high capacitance, which is something that is required in case of a capacitor. Similarly, different applications use these concept. So you're, as I said, you're always welcome to go through on how this concept of electrical double layer is used in multiple application. But since this course is not something that is more dealing with how this electrical double layer is used in the application, I'm going to limit the discussion of this here. So With this, I think the concept of electrical double layer is over. So majorly, I just wanted to discuss the difference and what is missing in the Helmholtz and what has been done to account for the real life process or the real life, you know, changes that happens within the system. Now we will move for modeling this diffusive double layer model. So last time we discussed about the Helmholtz electrical double layer. Over there we discussed about three different parameters. So can anybody tell me what are the three different parameters that we discussed last week based on this electric double layer formation? So one was your force, of course, that is the electrostatic force, and then the another one was your electric field. After that, we discussed about something very important, and we also solved one problem based on that. That is electric potential. So this is what we discussed in the last class on about the Helmholtz electrical double layer: force, electric field, and electric potential. So based on this, we take these as the three different, the this particular equations as the base, and we develop further more equation by incorporating other variables and stuff. So that's how we come to this diffusive layer model. We use that concept of electrostatic force, electric field, and electric potential, but with that we build up, with that we incorporate certain more variables and build up for our diffusive electric double layer model. So here it comes. So first we take up the Poisson's equation. So I hope you remember how we came up to this particular equation last class. So if I let me just write that. So we discuss the electric field as minus d psi by dx, right? So this was what was the expression for electric field. So from here we wrote electric field as nothing but, so we know that electric field is q by epsilon naught, or you can also say this as, now it will be fine. So this is how we wrote. So if you remember, f is 1 pi. Let me just show that. Yeah. So this was a problem that we solved in the last class. So here if you see, so if you see the part C, we wrote E is 1 by 4 pi epsilon Q1 by R square. So we took 4, we just rearranged this term as Q1 by 4 pi R square times epsilon. So Q by 4 pi R square is nothing but Q by A. So that we took it as surface charge density divided by your epsilon. So that is what we are writing here also. So Q by A epsilon times epsilon naught. So that will become your surface charge density by um, epsilon times epsilon naught. So you have, this is nothing but this is equal to minus differential of your electric potential. I mean, it's a gradient of electric potential. From here, if you just take one more derivative, you will get the Poisson's equation. So that Poisson's equation is represented as what, delta square psi equals to minus rho by epsilon times epsilon naught. Your rho is nothing but the charge density. So that is Coulomb per meter cube. Because we have taken another derivative, so it becomes charge density as rho, and this is your Poisson's equation. Now we need to express, if you see this charge density, we need to express this as a factor of this surface potential. So let me write this here. So your rho, that is the charge density, should be expressed as function of your psi. Psi is nothing but it's your potential, or you can also say it as surface potential. That will be more precise. So this rho, that is your charge density, should be expressed as a function of your surface potential. So for that, we express another term which is called as the Boltzmann's factor. So based on this Boltzmann's factor, we gave the equation, that is the concentration of the ions is nothing but is the concentration of the ions at an infinite distance from the surface that you are taking under consideration times exponential of minus Zi E psi by kT. So here your Ni infinity is nothing but the concentration of a particular ion that you are taking, or that is there in the electrolyte at a distance far away from the surface, infinite distance from the surface. So this can also be expressed or told as something called as a bulk concentration. So if you see here, if you see this diffusive layer, here you have a positively charged surface, here you have the solution, the diffusive layer. So after this boundary, if you see, all this the empty spaces that you have is nothing but is the bulk of your solution. So the concentration at any place here can be written as Ni infinity. So this is bulk. So this is nothing but this is your bulk, and the concentration here at the bulk can be expressed as Ni times infinity. So Ni is nothing but the concentration of your ion in the diffusive layer, and Zi is the valency of your ion. So suppose let's say you have NaCl, or yeah, NaCl is the best example. So that Na as well as Cl has a positive and negative charge, Na plus Cl minus ion. So they have a charge of +1 -1. So that is what Zi represents, specifically the valency of the ion that you are using for your electrolyte. Or if it in case it's magnesium sulfate or MgSO4, it will be +2, Mg +2, SO4 2 minus. So it will be +2 and -2. So similarly in case of, oh sorry, similarly in case of your aluminium chloride, it will be +3 -3. So like that. Your E is nothing but is the charge of an electron, because that +2 and -2 cannot be expressed as uh, just as a +2 and -2. They have to be converted into these many amount of coulomb. So for that we multiply that with the electron charge, and you have your phi, that is the potential, by kBt. Again, this kBt we are discussing for a long time. So kBt is nothing but, or KT is nothing but, it's your Boltzmann's factor, or it accounts for the thermal energy in the solution. So the thermal motion of your solution is expressed as a factor of Kt or Kbt. Both are same. So once you have the expression for the concentration of the ions, you can use that to calculate your charge density, that is rho. So rho is nothing but, it is Zi, or you can say summation, that is whatever all for the summation of all the different type of ions that is present in your solution. For all that you need to, so you need to what do you say, find the cumulative charge density for all the ions that is present in your solution, and you express that as Zi times E times Ni. So that is expressed as, so you know Ni is nothing but Ni times infinity, or Ni of infinite, or Ni, or the concentration of ions at infinite distance, times exponential of minus Z E psi by kT. So you are just uh, substituting this expression here. So let's keep this as equation 2. So you are just going to substitute the equation 2 in this expression, and this is what you get. So now you have the, so what we wanted to achieve was, we wanted to express the rho as a function of psi, that is your surface potential, and we have done that job. We have expressed rho as a function of psi, or your surface potential. Now use this expression 3 and substitute this expression in equation 1. So this is your equation 1, and this I am going to mark it as your equation 3. So this one will be nothing but, sorry, so substitute equation 3 in equation 1. So once you do that substitution, this can be written as dou square psi by dou x square equals to minus the expression for rho. So from here you can take certain things common, that is E. So E will always remain the same. So E by epsilon times epsilon naught. So here epsilon is nothing but it is your dielectric constant and epsilon naught is the dielectric permittivity of free space. This times this times the summation of Zi, that is your valency of the ion, Ni at infinity times exponential minus Ze psi by kT. So this equation is called as the Poisson-Boltzmann's equation. This equation, dou square psi by dou x square equals to minus E by epsilon naught times Zi Ni at infinity exponential minus Ze psi by kT is called as the Poisson's-Boltzmann's equation. So the term is because we have introduced this Boltzmann's factor into this Poisson's equation. So the equation number 1, the Poisson's equation. Equation number 2 is the Boltzmann's factor. Since we have substituted this 2 in 1, the equation is called as Poisson's-Boltzmann's equation. Now, we need to solve this. So this is a second order differential and we need to solve this equation. So in order to solve this equation, we take two assumptions. Since this has been discussed in the class, can anyone tell me what are the two assumptions that we had taken for this question? Or like what are the two assumptions that we have taken for solving this Poisson-Boltzmann's equation? Any idea? Any idea on what are the two assumptions for the Poisson's-Boltzmann's equation? I mean, for solving the Poisson-Boltzmann's equation that we took. Okay. So the two idea, so the two assumptions. Uh, so the two assumptions were one thing was the small surface potential, that is you can see here. So here you have the small surface potential. So we took this the value of psi as very small, so that this expression can be written out as something like what you see here, k square equals to E square epsilon naught kT times Zi square by Ni infinity. And then there is another one more assumption that we took. The second assumption was that the equation is for a was only for one dimension. So let me just write that here. The first thing was that we have taken only one dimension under consideration. Second thing is that the surface potential is very small. So these two assumptions were incorporated so that the such a big second order differential equation can be simplified to something what is seen here. These that is dou square psi by dou x square equals to k square psi. So k is nothing but it is called as kappa, and that is expressed as e square by epsilon naught kt zi square times ni at infinity. So the units of k or kappa is meter inverse, and so once you have this equation dou square psi by dou x square equals k square psi, you can bring this to the other side, and if you do the mathematics, you will get this expression. Psi equals to psi naught exponential of minus kappa times x. So this kappa or is also called as, can also be written as inverse inverse Debye length. This is one way usually it is called. Apart from that term kappa, I mean kappa is a symbol's name like lambda kappa. So this is also called as the inverse of Debye length. So this inverse of this Debye length will give you the Debye length. So Debye length is nothing but it is kappa inverse. So this is what is the linearized Poisson-Boltzmann equation for planar surface. Oh, sorry. This expression. So let me just highlight this. So this expression is called as the linearized Poisson-Boltzmann's equation for planar surfaces. Again, this is for a planar surface. For in the video lectures, there is a derivation for linearized Poisson-Boltzmann equation for a spherical surface also. So over there, it's just that the equation will be a bit different. So yeah, it will be like surface potential equals the potential is equal to the potential at the surface times rs, that is the radius of your sphere, times the small r, that is the radial distance that from radial distance where you want to measure the potential, times exponential of minus inverse of Debye length or kappa times the distance at which where you want to measure the potential minus rs, that is the radius of your sphere. So this is the expression. So this is for a sphere, linearized Poisson Boltzmann uh, equation for spherical surfaces. So this is for, just a second. So this is for a spherical surface, and then the equation that you saw here is for a planar surfaces. So again, depending upon the geometry under consideration, you need to manipulate the equations for deriving the appropriate you need to manipulate this particular equations for a planar surface for deriving the appropriate equations. So with this here, if you see, it's like these are all, again, as I keep saying, these equations were also discussed in the video lecture, but over there all the equations are derived in detail. So this is just like a gist of the important equations that you might be requiring for solving the problems. So this particular slide is nothing but it's just a collection of all the formulas or the important steps in the mathematical modeling of the diffusive double layer model. Based on this steps that you do, that you have here, we will be solving quite a number of problems today. In case if you have any doubts, then please let me know based on what we have discussed today. So next we have some. Okay. Okay, yeah. So we have few questions for today. The first question is, calculate the Debye lengths in 10 mole per meter cube and 40 mole per meter cube aqueous solution of zinc sulfate ZnSO4 at 298 Kelvin. So it's a very simple question which we are going to start with. They are just asking us to calculate the Debye length. So how do you solve this equation? How do you solve this problem? So we have the expression. So let me just give the expression beforehand. So this is the expression. From here, you need to calculate the Debye length. So since this question is given in terms of mole per meter cube, so that is already in terms of the concentration. So you just need to this Ni infinity will become Na times Ci naught. So you will have another one Avogadro number here. So the equation will be pretty bit different. So it will be like kappa square that is E square E square times Na. Na is nothing but your Avogadro number. Epsilon times epsilon naught, or I'll take it as epsilon. So epsilon is the dielectric permittivity of your medium, K T times Zi square, I mean the summation. Um, so that will be times Ci. So this will be the expression. The expression will now get modified. So it will not be. So here it is in terms of Ni, that is constant. So Ni is nothing but the concentration of the ion. But since the units are given in moles per meter cube, we need to uh, just convert this. So now the expression is something like this. So now you need to calculate for the Debye length. So Debye length will be the inverse of the value that you get for kappa. So kappa is inverse of Debye length. So you need to take 1 by inverse of Debye length will give you the Debye length. So what will be the expression for, I mean, what will be the answer for this? So let me just solve for this question because we have multiple questions today based on this concept itself. So let me just solve for the first one. Then from the second one onwards, I think it will be very easy. So first, we need to know what is the value of Z. So what is the valency of uh, Zn and SO4? Like the ions, once you put in the solution, it will the salt, once you put in the water, aqueous solution, so it will get split in terms of the ions. So what is the valency of that zinc ion and SO4 2 minus ions? Uh, I told the answer. So what are the valencies of zinc and sulfate ion? It's a yeah. So the valency is 2. So since this is a zinc sulfate is a symmetric solvent. So I hope you guys know what is symmetric and asymmetric electrolytes. So symmetric electrolytes will have same charge on cation and anion, and asymmetric electrolyte will have different charges. So again, as someone said rightly, so for here the Z value what you have is 2, and so your Ci for the first case A, is nothing but 10, 10 mole per meter cube. And then after this, yeah, so these are the two things that is going to change for your problem. So after this, whatever you have, that E square Na by epsilon kT will be the same. So here epsilon, the dielectric constant, you can take it as, since it's aqueous solution, so predominantly it will be water. So the dielectric constant will be same as that of the water, which is 78.4. So you can take this kappa square as, so E square Na by epsilon kT. E square, oh, times Avogadro number epsilon kT. So this value, so let me just write this value. So if you put this value, you will be getting, so the charge on one electron is 1.6 into 10 to the power minus 19 the whole square. This divide this times Avogadro number, that is 6.023 times 10 to the power 23 by your epsilon value, so that is 78.4. So again, as I say, please solve it with me so that it will be easy for you. K, that is your Boltzmann's constant, 1.38 times 10 to the power minus 23 times your temperature. So temperature is given here as 298 Kelvin, so 298. So if you simplify this, so let me just simplify and let's see what it comes, because if because this value is going to remain constant, so you can take this value always with you unless there is anything extra where they have told it's a concentrated solution or something else. This will remain the same, so it will be easy if right now you just simplify this and have that particular number in your mind. So let me just quickly do it in my personal calculator. So here we forgot one term. Dielectric constant is 78.4. So we need to multiply the value of epsilon also. That is 8.85 times 10 to the power minus 12, and the units are coulomb square per Newton meter square. So then the value will be, so the value is, if you have calculated, please tell me, or otherwise I can write. So the value is 5.404 times 10 to the power 15. So this is the value for this expression, E square Na by epsilon kT. So if you can remember this particular value, then the entire thing will become very simple, because after this it's just about plugging in whatever the values we have. So now, if I hope you have got the same answer. If you have any other answers, then please let me know, or otherwise I can progress. So okay, 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 okay. So since this answer is the same, and there were the calculations are fine, as far as I have also received one response. So I'm going to take this value 5.404. We will be using this for our other calculations also, so please keep this in mind. So k square value came out around, so it is 5.404 times 10 to the power 15. So this is same. Now we have Zi square times Ci. Here it's the summation. So you need to take care of both the ions that you have used. So the contribution comes from both zinc 2 plus as well as SO4 2 minus. So this will be 4 times Ci. So Ci is nothing but 10. So let's calculate what is the answer for this. Times 4. So it is coming around 216.16. So units are meter inverse. Now you know kappa square. So this is square of something. Oh, sorry, this will be meter power minus 2. So then the value of K will be root of this. So that is 14.7. Oh, so here we missed a 10 power 15 factor. So then the K value will be different. So it is 216.6, 0.16 times 10 to the power 15, the square root of this. So this is approximately uh, just as, so it will be more. So 4.64 times 10 to the power 8. Meter inverse. So this is the value of your inverse of Debye length. Now you need to get the value of Debye length. So that will be nothing but 1 by k. So 1 by k is nothing but the inverse of this value. So it is 2.15 times 10 to the power minus 9 times 10 to the power minus 9 meter. So this is the value of Debye length. So now you can solve for the next one and let me know the answer. I'll just give you approximately 3 to 4 minutes for solving the problem, and then let's see what's the answer. So this also you will progress in the same way. So just try out and let me know. So it will be something like, let me take this to the last line. So k square is nothing but 5.405 times 10 to the power 15 times, so zinc is 2, and so that will be 2 square 4 times 40 plus you will have another 4, so 4 is nothing but 2 square, right? So 4 times 40. So this is what is the value. Wait, just a second. Did we do this 2 times or? Oh, so we have 2 ions. So we took it. So in this previous case, we have taken it for only 1 ion. So you need to have for another ion also. So this will be again, there will be an extra factor of 4 into 10. So as I keep saying, this is what becomes the problem. Since there are multiple calculations to be done, sometimes we just don't, it skips out of the mind and then the value might be completely different. So as far as these questions are concerned, practice is a must, I would say. So now we need to recalculate here. So it is 5.404 times 80. So that will be exactly double. So 432.32. And the root will be, so this is approximately 6.575 into 10 to the power 8. So I will put it as 6.57 into 10 to the power 8. So now this is your kappa. So now you need to take 1 by k of that. So again, that times minus 1. So the answer is 1.52 times 10 to the power minus 9. So again, please. So the thing what we previously did was we didn't take into account that there are 2 ions like zinc 2 plus and SO4 2 minus. So that needs to be taken under consideration. So now the new value of your Debye length is 1.52 times 10 to the power minus 9 meters. So similarly here, if you see, then in the case B you will have, so 40 times 40 is 160, 160 plus 160 is 320 times 5.404 times 10 to the power 15. So K2 will be, let's calculate, 320 times 5.404 times 10 to the power of, so it is 320, it is 320 times 5.404. So that is 1729.28 times 10 to the power of 1728.29.28 times 10 to the power 50. So this is kappa square. So the value of kappa will be of this. So 1729.28. So this square, the square root of this number is 1.31 times 10 to the power 9 times 10 to the power 9 meter inverse. So this is the value of kappa. Now our inverse of Debye length. So the Debye length value is inverse of this. So that will be 7.6 or 0.76 nanometers or 7.6 times 10 to the power minus 10 meters, or you can write this as 0.76 nanometers. So this is the Debye length in case of if the concentration of the solution is 40 mole per meter cube, and in case if the concentration is 10 mole per meter cube, the answer is 1.52 nanometers. So you can see the difference that comes with the Debye length if the concentration of the solution increases. So the Debye length actually decreases with the increase in the concentration of your solution. So the question now here arises is what is actually the role of your concentration? I mean the physical significance on why the Debye length is decreasing with the concentration of the solution. So this will be an interesting question. So please think over this. We might take this up in the next class on understanding the variations of Debye length with concentration of electrolyte, the valency of the ion, and the temperature. So today we have seen the visible difference, but we need to understand the physical significance or the physical reasons or the scientific reason on why such change actually happens. So let me put this question. Why Debye length decreases with the concentration of the electrolyte? So let's move on to the next question. And now onwards it will become very simple since this factor was difficult for us to calculate every time. So it's up to you whether you want to remember this number, or is it okay if you are, if you're willing to calculate this, then it's fine. But this is just to make our calculation easier. From now, from this problem onwards, we will be taking this Na E square by epsilon kt as 5.404 into 10 to the power 15 in all cases of aqueous solutions at 298 Kelvin. However, again, if there is some other specification given in the question, or if there is any change, let's say for example, if the temperature is changing, or if the solution has a different dielectric constant, then please calculate this value once again. So the next question is something of a very similar concept, but it's just that the salt is different and we need to understand why, like how will the Debye length change if we change the salt. So the first question is here. I hope you will be able to calculate the value. So please solve parallelly with me and let me know the answer. So let me also start solving here. So kappa square again. Here I am not going to put that expression. Instead, since it's written aqueous solution, so I'm going to take this as I'm going to take the dielectric constant of KCl solution to be 78.4, same as that of the dielectric constant of water. So since E square Na epsilon kt is the same, I'm going to take the value as 5.404 times 10 to the power 15 . Now here the valency of KCl is 1, right? So 1 square, that will be 1. It's Zi square. Okay, let me just write for that one. So that it will be easy. Times Ci. So that will be nothing but 5.404 times 10 to the power 15. So Zi square will be nothing but, since KCl valency is 1, 1, 1 square is 1, 1 times Ci we have taken here as 40 mole per meter cube. So I'm going to put 40 plus the same thing for K as well as for Cl minus. So that will be again 1 times 40. So it will be 5.404 times 10 to the power 15 times 80. 40 plus 40. So the value is 432.32. 32 times 10 to the power 50. So this is the value of kappa square. So then the value of kappa will be nothing but square root of this. So that is 6.575 into 10 to the power 8. 6.57 times 10 to the power 8 meter inverse. So this is the value of inverse of Debye length. So Debye length will be inverse of this. So oh, the inverse of this will be 1.52 into 10 to the power minus 9, or you can write it as 1.52 nanometers. So if you compare the results for zinc sulfate ion at the concentration of 10 mole per meter cube, we got the value as 1.52. But here for 40, we are getting 1.52. Or you can say at the same concentration of 40 mole per meter cube, the KCl had a greater Debye length compared to zinc sulfate, which had 0.76 nanometers. So the question is, if the so you can conclude this, if the concentration of the electrolyte ion is kept same, so we can write it here. If the concentration is kept same, then the Debye length decreases with the valency of ion. Correct? So because KCl is having more Debye length compared to zinc sulfate. So valency of zinc sulfate is greater compared to KCl, like plus KCl has plus 1 and KCl has plus 1 minus 1, zinc sulfate has plus 2 minus 2. So zinc sulfate has more valency, but then its Debye length is less compared to KCl. So of course this is it is following the trend, because if you see where is this, yeah, so if you take the root of this, you will be getting, so focus on this expression, yeah. So if you take the root of this particular expression, yeah, here, so you'll be left out with E divided by root of epsilon kt times root of zi square times ci or ni at infinity. So zi square will be taken out as zi. This is K, that is your kappa. So now you need to do the inverse. So the kappa inverse will be, I think it is better to write and show. So, so if you take the square root, it will become E. E is nothing but the electric charge. So E times Na by epsilon kt whole power 0.5 and then you have the summation coming up. So so the summation will be, so it will be Zi square times Ci, right? So if you see here, this Zi square Ci, you can take that Zi square outside the bracket. So you can take this outside the bracket. So if you do that, then kappa can be written as Zi times the charge of the electron times Na by epsilon Kt whole power zero point 0.5 times, then you will only be left out with, you get well, you cannot write it this way, so let me just express it differently. So you can write this expression as, so it will have Ci whole power 0.5 times Zi. So this is for kappa. So now you need to take the Debye length is nothing but 1 by kappa. So that will be, so this expression is nothing but 1 by the entire, or you can write this, you can write this as EKT by Na whole power 0.5 times 1 by Zi times 1 by this Ci power 0.5. So this is what something the Debye length equation will look like. So this Debye length is nothing but it's inversely proportional to your valency of the ion. So that's what we also concluded it from this solving. So as the, if you keep the concentration same, and if you are going to change, if you are going to increase the valency of the ion, then the Debye length will decrease. So one of the main reasons why this actually happens is because, so when you have greater valence of ion, the ideal layer will be much thinner, because greater valency of the ion will, the reason why it will be thinner is because it will be easy to compensate the charge difference on that surface. So that is the reason a thinner layer is enough to compensate that charge. So that is, so since the valency of the ion is greater, it can compensate the charge easily. So that is the reason the electrical double layer is thin, which is not the case of a single valent ion. So that compensation of the charge of the surface is something which determines the thickness of the double layer, and that is determined by your valence of the ions. So this is about the calculation of Debye length and its variation with the valency of the ion. Now we have another one part where we need to see how does the temperature have an effect over the Debye length. So let's just use this expression first to understand how will the variation be before we solve. So we have seen that Debye length is directly proportional to temperature. So as temperature increases, the Debye length will increase. So this is because as you increase the temperature, the diffusion of the molecules will be more, the thermal motion will be more. So since the thermal motion is more, the formation of the double layer will be higher or thicker, because there will be lots of ions which will be like within the vicinity, but they will be in the thermal motion. So due to which the Debye length will increase. So let's see how far it increases. So we just need to change this particular parameter. So here, as I said, since the temperature is increasing, we will not be able to use this 5.404 into 10 to the power 15. We need to change the value. So let's see this. Uh, okay, it's fine. So that is kappa square. So you have your now E square Na. So let me use this expression. I'll just change the temperature alone here. So here instead of 298, we are supposed to write 323. This times Zi squared times Ci. So since all this is going to be the same, it is 40 plus 40. Now we need to calculate for this expression. So please calculate along with me. Since this is a big expression, I'm going to use my personal calculator. Here again, as it is an aqueous solution, you can keep the dielectric constant as 78.4. So that won't be, I mean, that's not a issue. So any answers? So I have got an answer. Let me just type it here. You just let me know whether it is correct or not. So it is 4.98 times 10 to the power 50. It's 4.985. So if you have any other answers, let me know. So this value will be 398.8 times 10 power 15. 398.8 times 10 to the power 15. So this is kappa square. So you need to calculate the value of kappa. The square root. So 6.315 into 10 to the power 8. Meter inverse. So please remember the units. Units of kappa is meter inverse, and Debye length, that is inverse of this, is your Debye length, or the Debye length units is meter. So in case if you get confused which is the Debye length, whether it is K or kappa inverse, if you remember the units, then it will be easy. So yeah, so your K kappa, your Debye length is nothing but inverse of this. So it is 6.315 times 10 to the power 8. It is 1.58 nanometers, or 1.58 into 10 to the power minus 9 meters, or 1.58 nanometers. So this is the value of the Debye length. If you see, we got, of course, the difference is not that very high. I mean, if you see from our from the human perspective, 1.52 and 1.58 at the macro, from the macroscopic point of view, it's not a considerable difference. But when you go inside the molecular level, this is the huge difference that comes, and this is something, you know, is what is in trend with what we expected previously. So we said that if the temperature is increasing, so you see here the expression. So we told that if the temperature is increasing, then the Debye length will increase, and that's what has happened. Since the temperature was increased from 298 to 323, the value of Debye length increased. The difference is less because the temperature difference is also less. If suppose the temperature difference is a lot more, then again considerably the Debye length value will also be more. But what we want to learn from here is, if the temperature increases, the thermal motion, so some amount of the thermal energy is imparted to the molecules. Because of that thermal energy, they will be in the thermal motion, there will be a diffusion, and due to which the double layer will be more, because many ions will be present near the surface. So due to which the thickness of the double layer will increase. So I hope if there are any doubts, do let me know before we progress for this question. Again, the last three are quite easier. Any any questions? Anyone? The last three questions are something more like questions from, or at least the question number 3 and 4 are from competitive exams like CSIR net. So you can like really get to know that these. Uh, Sorry, there was a network issue. So let me just present once again. So yeah, we were here. Yeah, so if you have any doubts for the previous two questions, let me know, or we can go for this one. So, okay, if you have any doubts, then let us discuss at the end. Um, so let's see this question. Choose among the electrolyte solution that has the smallest Debye length at 298 Kelvin. So any answers on what could be this? See, because if you see here, previously we discussed questions related to symmetric electrolytes. Here we also have asymmetric electrolytes. So any guesses on what could be the answer? A, okay, okay. Let's see what is the answer. So again, since it is all aqueous solution, so let me mention that condition here. Aqueous solutions. So here we can keep that first term as constant, e square na by epsilon naught kt as same. So with that we can just change the second part of the expression, that is your zi square times ci, and then calculate. So let's see for first for the A option. So I'm going to keep that 5.404 as some constant b. I'm going to keep this as b. So with this, the value of k square will be b times, um, so again concentration I'm going to keep it as c. Let's just take some variables so as to make sure that it is easy for us to know, I mean calculate the values. So it is b times zi square. So for NaCl it is 1, right? So it is 1. 1 square is 1. Again 1 times c plus, so this will be nothing but b into 1c plus 1c, that is 2c. So you can write as 2bc. You can keep it as 2bc. So this is with option A. So 2bc, so that will be, so kappa will be root 2, or yeah, root 2 bc, or 1.414 bc power 0.5. uh, yeah. So k will be 1 by 1.414, so times bc whole power 0.5. So if you keep this as bc power minus 0.5, so we just need to know what is 1 by 1.414. 0.707. This is Debye length. 0.7 bc power minus 0.5. So this is option A. Option B will be B times again. So it is Na to SO4. So for Na to SO4, Na is 2, and SO4, sorry, Na plus SO4 2 minus. So it will be 1 times C plus 2 times C. So it will be 1 square. So that will be 1. 1 times C plus SO4 2 minus. So that will be 2 square. So 4. So this is nothing but 1c plus 4c, that is 5. So 5bc. So k will be root 5. So that will be root 5. 2.23. Again, this BC power 0.5. So Debye length will be nothing but, it will be like BC power 0.5 divided by 2.23. So 1 by 2.23 is 0.44. 0.44 BC power minus 0.5. So this is about option B. So option C also let's calculate quickly. So again it is B times. So it is AlCl3. So aluminium will have 3 and Cl will have 1. So 3 square. So 3 square is 9 plus Cl is 1. So 1 square is 1. So this will be nothing but 10 Bc. So kappa will be nothing but root 10. So root 10 is 3.16 BC power 0.5. So then the Debye length will be nothing but 1 by 3.16. So 0.316. 0.316 times BC power minus 0.5. Now you have magnesium phosphate. So Mg3PO4 twice. So Mg2 plus and PO4 3 minus. So if you let me take this expression and modify it. So let me first remove all this. So Mg2 plus, so 2, so 2 square is 4 plus PO4 3 minus, so 3 square that is 9. So that will be like totally it is 13 BC. So root of 13 is 3.6 and 1 by 3.6 is 0.27. So this is, so if you see if the BC factor is constant, so BC power minus 0.5 will also be constant. So if you see with that, if you see the last option D has a minimum value of Debye length. So I think somebody told A, so it option is D. So you can think it from, again you can use this equation. That is a more lengthier way to solve. But if you see this equation, I hope you are able to see this equation. You can see that it is Debye length is 1 by Zi times, or you can write it like 1 by Zi times. You can write it something like this. So Debye length is inversely proportional to Zi and Ci power 0.5. So which means that as the value of Z increases, your Debye length is going to decrease. So with that concept, if you see for NaCl it is 1 and 1, for Na2SO4 it is 1 and 2, for AlCl3 it is 3 and 1, but for Mg3PO4 twice it is 3 and 2. So that electrolyte has a highest Zi value. So since it has highest valency, the Debye length is going to be the least. So instead of doing this process, you can just use this equation and then just, minimize the entire effort. So I hope there is, if there is any doubts, then let me know. But the concept is this: higher the valency, the thinner will be the ideal, because the charge compensation at the surface is going to happen sooner. So next we have one question, but if you have any doubts, then please let me know, or otherwise we can progress. Let's solve question number 5 first. So any doubts? If not, then let's see question 5, because question 4. Uh, so this is more based on charge. So which one will have, so NaCl is Na plus and Cl minus, right? So that means it will have more size compared to Mg3 and PO4. So yeah, that is one way to say, but you can also do that, because Mg3 plus will be smaller compared to that one, so that Debye length will be less. But yeah, that is one way to say. But but it is better to use this equation, so that it is more based on the charge. So you're just correlating charge and then the size of the ion. Yeah, so that is, I guess it's fine. Okay, so we have one question before we close our session for today. So it's about spherical surfaces. So till now we discussed more on uh, what do you say, planar surfaces. So this is about spherical surfaces, and again I guess it's a very simple question. They are saying a spherical particle is having a surface potential psi naught of 23 millivolt, is present in an electrolyte solution where the Debye length is 23 nanometers. Okay. Calculate the potential at a distance of 200 nanometers if the radius of the sphere is 5 micrometers and 25 micrometers. So let's take the expression for spherical surfaces. So here, so this expression again is valid because your surface potential is 23 volt. So if you remember in the video lectures, we use that, uh, so we use this expression here. Psi is less than kT. So if you use this expression and calculate at 298 Kelvin, your psi value should not be greater than 25.7. So if it is greater than 25.7, then this expression is invalid. So psi should be less than 25.7, then the expression is valid. then the above expression is valid. If not, this expression becomes invalid. So please keep that in mind. So since here it is given that the psi naught value is 23, so 23 is well below 25.7, so we can use this expression. So since this expression is valid, I think it's now more about substitution. So let's just substitute. So this is 23 millivolt times Rs. Rs is radius of the sphere. So I'll do one part, you can do the other part and let me know the answer today or by next week. It is 5 micrometers and divided by small r. So small r is basically the place at which you want to find out what the potential is. So that is 200 nanometers or zero point 0.2 micrometers times exponential minus, we need kappa but we have 1 by kappa, so that will be 1 by 23 nanometers, or I'm going to write that value here, 1 divided is 0.043 times, since it is nanometer you will have a 10 power 9 at the top, so it is r minus rs. So r is 200 nanometers, your rs is 5 micrometers, so we need to convert. So if you convert everything into meter, it will be 5 into 10 to the power minus 6 divided by uh, 200 nanometers. So 200 into 10 to the power, okay, it's 0.2. So it will be cancelled out. So it's 5 divided by 0.2. So this is fine. It's just only here. So if you calculate this expression, we getting W equals to 23. 5 by 0.2 is 25 times exponential. So this I'll calculate. So it is, so it will become plus. So 0.043 times 4.8 times 10 to the power 3. So 10 cube. So your potential is, just let me, please solve it. If you know the answer, let me know, or otherwise I'll give the answer here. So what is the answer? So please solve for this because I've given everything. You just need to solve. Please solve this. We will take up this question again in the next class. I mean, I'll be asking the answers in the next class. So please solve it and keep it ready. We have one small question to discuss. So for this, you are going to say the answer. What will be the ratio? You have three symmetric. Again, symmetric means the cations and the anions have the same charge. So they are in the same concentration, but then their dielectric constant are different. 4, 25 and 81. Now we need to say the ratio of the Debye length for the three electrolyte solutions. So what could be the ratio? So you can, I mean, yeah, you can use this expression and then tell what could be the ratio. I'll just copy paste this equation there. So your epsilon, or you can say epsilon times epsilon naught, or dielectric constant times epsilon naught whole power 0.5. So what is the ratio? It's directly proportional. I guess I've given the answer now. So you just need to tell me what could be the ratio. So Debye length is something proportional. So it's proportional to dielectric constant whole power 0.5. We have a proportional thing. Yeah. So this is the idea. So your Debye length is going to be proportional to the dielectric constant whole power 0.5. And since all the three are symmetric, same concentration, so your Zi Ci whole power 0.5 will be the same. Na is the same. Kt is the same. Epsilon naught is the same. So it just Debye length is directly proportional to dielectric constant whole power 0.5. So what is the ratio now? Or what is, yeah, so what is the ratio? It's simple. I mean, yeah, so that's correct. So dielectric constant is given as 4, 25 and 81. So that will be nothing but 4 power 0.5 and 25 power 0.5 and 81 power 0.5. So that is 2 is to 5, 25, root of 25 is 5 times 81 whole power point 5 is 9. So the ratio will be 2 is to 5 is to 9. So this is one of the questions that came in the CSR net exam somewhere in one particular year. So it's just that if you know the expression, you can just simply use this particular relation. Debye length is directly proportional to dielectric constant 4 power 0.5, and then you will get the answer. So please solve for the question number 5, the value, and let me know in the next class. So if next live interaction session. So if you have no doubts, then, or if you have any doubts, please ask me, or else we can conclude our session for today. So so if there are no doubts, then okay, I'll just conclude. Thank you everyone for joining the live interaction session today. If you have any doubts, you are welcome to email me. My email ID will be available in the PPT that will be uploaded in the Google Excel sheet, which is there in the course page. You can access that. It will be at the left bottom corner of the NPTEL course page for this collides and surfaces. You are also welcome to use the Q&A section to post your doubts. So I would like to take this as an opportunity to thank Professor Basavraj as well as the NPTEL team for providing me this opportunity to interact with you all this Sunday afternoon. Next live interaction session will be on 8th of September from same 5 p.m. to 7 p.m. So that's all for today. Thank you for joining and